Good evening. As you settle into this moment of quiet contemplation, prepare yourself for a journey unlike any other. Tonight, we're venturing to the very edge of everything we know, to the boundaries where space and time themselves become concepts almost too vast for the human mind to grasp. We're going to explore the most profound question in cosmology: what lies at the edge of the universe, and what exists beyond everything we can see? This is not just a story about distance or size. It's a story about the limits of knowledge itself, about horizons that exist not because of what's there, but because of fundamental laws woven into the fabric of reality. It's about regions of space that are forever beyond our reach, galaxies that will vanish from view as if they never existed, and the haunting possibility that our entire observable universe might be just one bubble in an infinite sea of other universes. Before we begin this cosmic odyssey, I invite you to like this video and subscribe to the channel. Your support gives me the motivation to continue bringing you these explorations of our magnificent cosmos. And now, let's drift into the dream of exploring the vast universe together with Astromind. So relax, breathe deeply, and let your imagination carry you to the furthest reaches of space and time, to places where even light itself cannot go. Chapter 1: The Paradox of an Expanding Horizon. Imagine standing on a beach at dawn, watching the horizon where the ocean meets the sky. No matter how far you walk, that horizon moves with you, always the same distance away, always just out of reach. The cosmic horizon works in a similar way, but with a twist that makes it far stranger and more profound. When we look up at the night sky, we're not just seeing space, we're seeing time. The light from the stars has traveled for years, decades, centuries, or even millions of years to reach our eyes. The farther away an object is, the older the light we're receiving from it. This simple fact creates one of the most mind-bending features of our universe. We live inside a sphere of visibility, bounded not by walls or barriers, but by time itself. This sphere is called the observable universe, and its radius is approximately 46.5 billion light-years in every direction. Wait, you might think, if the universe is only about 13.8 billion years old, shouldn't the observable universe have a radius of 13.8 billion light-years? That would make sense if space were static, unchanging. But space is not static. It's expanding, and it has been expanding since the moment of the Big Bang. Here's where things get beautifully complex. When we observe a galaxy that appears to be, say, 10 billion light-years away, we're seeing light that left that galaxy 10 billion years ago. But in those 10 billion years, space itself has been stretching. The galaxy has been carried along with that expansion, moving farther and farther away. Today, that same galaxy is actually much farther than 10 billion light-years from us. In fact, it might now be more than 20 billion light-years away, even though the light we're seeing from it is only 10 billion years old. This is why the observable universe is so much larger than you might expect. The most distant light we can see, the cosmic microwave background radiation, was emitted about 13.8 billion years ago, when the universe was only 380,000 years old. But the matter that emitted that light has been moving away from us ever since, carried by the expansion of space. Today, that matter is approximately 46 billion light-years away. The boundary of the observable universe, often called the particle horizon, represents the farthest distance from which light has had time to reach us since the Big Bang. Beyond this horizon lies more universe, regions of space that exist but whose light simply hasn't had enough time to reach Earth yet. Every day, as the universe ages by one more day, this horizon expands by approximately 1 light day, revealing slightly more of the cosmos to our view. But there's another horizon, one that's even more profound and, in a sense, more final. It's called the cosmic event horizon, and it marks a boundary of a different kind. This horizon represents the farthest distance at which events happening right now could ever, even in the infinite future, send us a signal that we could receive. To understand this, we need to think about the expansion of the universe. For most of cosmic history, gravity was the dominant force on large scales, working to slow down the expansion that began with the Big Bang. If gravity had remained dominant, the universe might have eventually stopped expanding and even collapsed back on itself in a big crunch. Or it might have continued expanding forever, but at an ever-slowing rate. But something changed. In the late 1990 seconds, astronomers studying distant supernovae made a shocking discovery. The expansion of the universe is not slowing down, it's speeding up. Galaxies are not just moving away from each other, they're accelerating, moving faster and faster as time goes on. This acceleration is attributed to something called dark energy, a mysterious form of energy that appears to permeate all of space. Dark energy makes up about 68% of all the energy in the universe, yet we have no idea what it really is. What we do know is that it's causing space to expand at an accelerating rate, and this has profound implications for the cosmic event horizon. Because of dark energy, galaxies that are sufficiently far away are receding from us faster than the speed of light. Now, this doesn't violate relativity because nothing is moving through space faster than light. Rather, space itself is expanding, carrying galaxies along with it. And here's the crucial point. If a galaxy is far enough away that the space between us and it is expanding faster than the speed of light, then light leaving that galaxy right now will never reach us, ever. The cosmic event horizon, currently about 16 billion light-years away, marks this boundary. Any event occurring beyond this distance today will remain forever invisible to us, no matter how long we wait, no matter how powerful our telescopes become. The light from those events is simply swimming upstream against an expansion that's too fast for it to overcome. And here's where it gets even stranger. The cosmic event horizon is not expanding with time, it's actually shrinking in terms of which galaxies will remain visible to us. Right now, we can see galaxies that are well beyond the current event horizon because we're seeing them as they were in the past, when they were closer to us and within our visible range. But as time goes on, those galaxies will fade from view, their light stretched to longer and longer wavelengths by the expansion of space, redshifted into invisibility. In the far future, in about 150 billion years or so, the observable universe, as seen by any astronomers living in our galaxy, will consist of just our local group of galaxies. Everything else will have receded beyond the cosmic event horizon, disappeared from view as if it never existed. Future astronomers will look out into space and see, essentially, nothing. No distant galaxies, no cosmic microwave background, no evidence of the Big Bang or the expansion of the universe. They'll live in what appears to be an island universe, isolated in an empty cosmos. This is one of the most sobering realizations in cosmology. Not only is there an edge to what we can see, but that edge is closing in. The universe is not just vast beyond comprehension, it's also gradually becoming invisible to itself, hiding most of its contents behind an ever-shrinking horizon. But what's beyond that horizon? What exists in the regions of space that we can never see? To answer that, we need to think carefully about what the universe really is and how it came to be. Chapter 2. The Infinite Ocean Beyond. When we say the universe, what do we really mean? For most people, universe means everything that exists. But in cosmology, we've had to become more precise with our language. The observable universe is just that, the part we can observe. But is there more beyond? And if so, how much more? The most straightforward answer, the one suggested by our best observations and theoretical models, is that yes, there is vastly more universe beyond our observable horizon. In fact, the universe beyond what we can see might be infinite in extent. Let's think about this carefully. The observable universe is a sphere centered on Earth, with a radius of 46.5 billion light-years. But there's no reason to think that space simply ends at that distance. The laws of physics, as far as we can tell, are the same everywhere. Galaxies, stars, and planets don't suddenly stop existing just because they're too far away for their light to have reached us yet. In fact, every other observer in the universe sees their own observable universe, a sphere of the same size but centered on their location. An observer in a galaxy 10 billion light-years from Earth would see many galaxies that we can't see, and vice versa. Their observable universe would overlap with ours, but extend into regions forever hidden from our view. This leads to a remarkable conclusion. The universe is almost certainly much larger than the observable universe. But how much larger? Twice as big? 10 times? 1,000,000 times? The answer might be that it's infinitely large. Current observations of the cosmic microwave background and the large-scale structure of the universe suggest that space is geometrically flat or very close to it. In general relativity, the geometry of space can take one of three forms: positively curved like the surface of a sphere, negatively curved like a saddle, or flat like a sheet of paper. Observations from satellites like the Planck mission have measured the curvature of space with exquisite precision, and the data indicate that the curvature is 0 to within a margin of error of about 0.4%. If space is truly flat and extends indefinitely in all directions, then the universe is infinite. It has no edge, no boundary, no outside. You could travel in a straight line forever and never reach an end. This is difficult to visualize because we're used to thinking of space as something that exists within a container. But in cosmology, space is the container. There's nothing for it to exist within. An infinite universe has some strange implications. If space extends forever and is filled more or less uniformly with matter on large scales, as we observe it to be in our region, then there are an infinite number of galaxies, an infinite number of stars, an infinite number of planets. And if quantum mechanics is correct, and there are only a finite number of ways to arrange matter and energy within any given region of space, then, in an infinite universe, every possible arrangement must repeat infinitely many times. This means that somewhere out there, far beyond our cosmic horizon, there's another galaxy that looks exactly like the Milky Way. In fact, there are infinitely many such galaxies, and in one of them, on a planet that looks exactly like Earth, there's someone who looks exactly like you, living a life identical to yours down to every detail. And there are other copies where just one thing is different, where you made a different choice at some point, where history unfolded slightly differently. This sounds like science fiction, but it's a straightforward mathematical consequence of an infinite universe with finite possible arrangements. The number of ways atoms can be arranged in a region the size of, say, the observable universe is enormous but finite. It's been calculated to be something like 10 to the power of 10 to the power of 124. That's a 1 followed by more zeros than there are atoms in the observable universe. But it's still finite. In an infinite space, even that incomprehensibly large number is eventually exhausted, and patterns must repeat. Of course, we can never verify this directly. Those copies of you, those doppelganger Earths, are forever beyond our reach, hidden past horizons we can never cross. They're part of what some cosmologists call the quilted multiverse, a single, infinite space with repeating patterns, as opposed to separate, disconnected universes. But infinity is just one possibility. Space could also be finite but unbounded, which sounds contradictory but makes sense in the context of general relativity. Think of the surface of a sphere. It's finite in area, but it has no edge, no boundary. You can walk around the entire surface of the Earth without ever falling off an edge or reaching a wall. The surface is two-dimensional and curved in a third dimension. Similarly, our three-dimensional space could be curved in a fourth spatial dimension, forming the three-dimensional equivalent of a sphere's surface. Such a space would be finite in volume but would have no boundary. You could travel in what seems like a straight line through this space and eventually return to your starting point, like traveling around the Earth and coming back to where you began. In such a universe, if you looked far enough in one direction, you might actually see the back of your own head, or rather, the back of your head as it was billions of years ago when that light began its journey around the universe. This seems bizarre, but several cosmological models propose exactly this kind of topology. There's even evidence, though controversial, that the universe might have such a structure. Some astronomers have looked at patterns in the cosmic microwave background and claimed to see hints of wraparound, signs that the universe might be smaller than the observable universe, so that we're actually seeing the same regions of space in multiple directions, viewed from different angles. Other researchers dispute these findings, and the question remains open. But whether the universe beyond our horizon is infinite or merely enormously large but finite, one thing is clear: there's vastly more universe out there than what we can see. Our observable universe, as large as it is with its 2 trillion galaxies, is likely just a tiny fraction of the whole, perhaps an infinitesimal fraction, and that's just considering the universe as a continuous expanse of space. The story gets even stranger when we consider the possibility of other universes entirely, separated from ours, not by distance but by the very structure of space-time itself. Chapter 3: The Inflationary Multiverse. To understand how we might be just one universe among many, we need to go back to the very beginning, to the first fraction of a second after the Big Bang. This is where the theory of cosmic inflation comes into play, and it's where our concepts of space, time, and universe become almost impossibly strange. In the standard Big Bang model, the universe began in an extremely hot, dense state, and has been expanding and cooling ever since. This model explains a great deal about the universe we observe today, from the cosmic microwave background to the abundance of light elements like hydrogen and helium. But it also has some puzzles. One puzzle is called the horizon problem. The cosmic microwave background, the afterglow of the Big Bang, looks remarkably uniform in all directions. Its temperature is the same to within 1 part in 100,000 no matter where you look in the sky. This is surprising because, according to the standard Big Bang model, regions of the universe that are on opposite sides of the sky were never in causal contact with each other. They've never had a chance to exchange energy or information, so why should they have the same temperature? Another puzzle is the flatness problem. As we mentioned, measurements show that space is remarkably flat, with curvature very close to zero, but in the standard Big Bang model, a flat universe is unstable. Any slight deviation from perfect flatness in the early universe should have been amplified over time, leading to a universe that's either dramatically positively curved or negatively curved. Yet we see something extremely close to flat, which seems to require fine-tuning of the initial conditions to an almost unbelievable degree. In 1981, physicist Alan Guth proposed a solution to these problems: cosmic inflation. According to inflation theory, The universe underwent a brief period of exponentially rapid expansion in the first tiny fraction of a second after the Big Bang. During this inflationary epoch, which lasted perhaps from 10 to the power of negative 36 seconds to 10 to the power of negative 32 seconds after the Big Bang, the universe expanded by a factor of at least 10 to the power of 26, and possibly much more. This rapid expansion would have stretched the universe from smaller than an atom to potentially larger than the currently observable universe, all in less time than it takes light to cross an atomic nucleus. Any initial curvature would have been stretched out flat, like inflating a balloon to enormous size makes any small patch of its surface appear flat. And regions that were initially close enough to be in thermal equilibrium would have been stretched to opposite sides of the observable universe, explaining why they have the same temperature. Inflation also makes specific predictions about the tiny fluctuations in the density of matter in the early universe, fluctuations that would later grow under gravity to form galaxies and clusters. These predictions match observations of the cosmic microwave background with remarkable precision, giving cosmologists confidence that something like inflation really did occur. But inflation has an unexpected consequence, one that its early developers didn't fully appreciate at first. It turns out that once inflation starts, it's very difficult to make it stop everywhere at once, and this leads to eternal inflation and the multiverse. Here's how it works. Inflation is driven by a quantum field called the inflaton field, which has potential energy that causes space to expand rapidly. As the inflaton field rolls down its potential energy curve, inflation eventually ends, and that energy is converted into ordinary matter and radiation, creating the hot, dense state we call the Big Bang. But quantum fields are subject to quantum fluctuations, random variations that occur on microscopic scales. During inflation, these quantum fluctuations can cause the inflaton field to fluctuate as well. In most regions, the field rolls smoothly down its potential and inflation ends. But in some regions, quantum fluctuations can actually push the field back up the potential, causing inflation to continue in those regions even as it ends in others. The regions where inflation continues expand exponentially, becoming vastly larger than the regions where inflation has ended. Within each inflating region, the same process repeats. Most areas end inflation, but some continue. This creates a never-ending cascade of inflating regions, producing non-inflating bubble universes like ours. The result is called eternal inflation because once it starts, it never entirely stops. It produces an infinite, fractal multiverse, with each bubble universe being a separate domain with its own Big Bang, its own expansion history, its own galaxies and stars. Our entire observable universe would be just one such bubble, created when inflation ended in our particular region of space. This is a profound shift in perspective. If eternal inflation is correct, then when we ask, what's beyond the edge of the observable universe? One answer is more of our universe, stretching perhaps to infinity. But another answer is, eventually, you reach the edge of our bubble and enter the eternally inflating space beyond, where quantum fields writhe and space-time expands faster than anything can traverse it. And scattered through that eternally inflating space are other bubbles, other universes, each with its own Big Bang, each potentially infinite in extent, each forever causally disconnected from ours. We can never see these other bubble universes because they're separated from us by regions of eternally inflating space. Light emitted from one bubble can never reach another because the space between them is expanding too rapidly. It's a permanent separation, more complete than any distance measured in light years. Moreover, the physical conditions in each bubble universe might be different. The way inflation ends and converts the inflaton field's energy into matter and radiation might vary from bubble to bubble. Different bubbles might have different values for fundamental constants of nature, different types of particles, even different numbers of spatial dimensions. This is where inflation connects with string theory, the leading candidate for a theory of quantum gravity. String theory doesn't predict a single unique set of physical laws. Instead, it has something called the landscape, a vast collection of possible vacuum states, perhaps 10 to the power of 500 of them or more. Each vacuum state corresponds to a different set of physical laws and constants. If inflation is eternal and the string theory landscape is real, then different bubble universes could settle into different vacuum states. Some would have strong forces, some weak. Some would have electrons much lighter than ours, some heavier. Some might have only 2 spatial dimensions, others might have 4 or 5. Most would be radically different from our universe, inhospitable to any form of life or structure. Our universe, with its particular values of physical constants that allow for atoms, chemistry, planets, and life, would be just one outcome among countless others. We find ourselves in this particular universe not because it's special, but simply because this is one of the universes where beings capable of asking the question can exist. This is called the anthropic principle. We observe the universe we do because the very act of observation requires observers, and observers can only arise in universes with certain properties. This multiverse picture raises profound questions. If there are infinitely many universes with all possible properties, does our universe have any meaning? Is there any point to cosmology if every possible outcome is realized somewhere? Can we even test these ideas scientifically, or do they fall into the realm of untestable metaphysics? These questions have sparked intense debate among cosmologists and philosophers. Some embrace the multiverse as a natural consequence of well-established physics. Others reject it as speculation that goes beyond what science can address. The debate continues, but one thing is clear: the simple question, what's beyond the edge, has led us into territory where the very concepts of space, universe, and existence itself become fluid and strange. Chapter 4: The Topology of Everything. Let's step back for a moment and think about the shape of the universe in a different way. We've talked about whether space is infinite or finite, whether it's flat or curved, whether there are multiple universes beyond ours. But there's another aspect to consider: the topology of space, which describes how space is connected to itself. Topology is a branch of mathematics that studies the properties of shapes that don't change when you stretch or bend them without tearing. A coffee cup and a donut have the same topology because you can smoothly deform one into the other. Both have one hole. But a sphere and a donut have different topologies. There's no way to turn a sphere into a donut without tearing a hole in it. The universe could have interesting topology even if it's geometrically flat. Imagine a flat 2-dimensional universe like a sheet of paper. You could roll that paper into a cylinder by connecting 2 opposite edges. An inhabitant of this cylindrical universe would think they're living in flat space, because locally, everything looks flat. But if they traveled far enough in one direction, they'd come back to where they started, having circled the cylinder. You could also connect both pairs of opposite edges, turning the flat sheet into a torus, the surface of a donut. Again, locally, space is flat, but globally, it's finite and multiply connected. There are many different ways to connect space to itself, creating different topologies with wildly different global properties while keeping the local geometry flat. Our 3-dimensional space could have analogous structures. The simplest possibility is that space is simply infinite and flat, extending forever in all directions with no connections or twists. But space could also be a 3-dimensional torus, finite in volume, but with no boundary, where traveling far enough in any direction brings you back to your starting point. Or space could have even more exotic topologies. It could be a Klein bottle, a shape where the inside connects to the outside. It could be a Poincaré dodecahedral space, where space wraps around itself in a complex pattern related to a 12-faced polyhedron. Mathematicians have catalogued hundreds of possible topologies for three-dimensional spaces, and any of them could, in principle, describe our universe. If the universe has one of these non-trivial topologies, and if it's small enough, we might be able to detect it. Here's how. Imagine the universe is a three-dimensional torus, and its circumference in one direction is, say, 20 billion light-years. If you look in that direction, you'd see light that has travelled all the way around the universe and come back from the opposite direction. You'd see the same galaxies twice, once in their normal position and once as they appear from the opposite direction, like looking at the back of your head in a series of mirrors. Astronomers have searched for such repeating patterns in the distribution of galaxies and in the cosmic microwave background. So far, they haven't found any convincing evidence of non-trivial topology on scales smaller than the observable universe. This doesn't mean space has simple topology. It might just mean that the wraparound scale is larger than what we can currently observe. But the possibility remains open. Space could loop back on itself on scales far larger than the observable universe. In that case, the universe beyond our horizon would eventually curve back toward us from the opposite direction, travel far enough in one direction, and you'd eventually see Earth from the other side, though you'd be seeing Earth as it was billions of years ago when that light began its journey around the cosmos. The topology of the universe also connects to the question of whether space is infinite. A flat space can be either infinite or finite, depending on its topology. If space is a simple, infinite expanse with no connections, it's infinite. But if it's a torus or other closed manifold, it's finite, even though it has no boundary. Interestingly, current observations suggesting that space is flat don't tell us whether the universe is infinite or finite. Both are consistent with a flat geometry. We'd need to detect the topology directly by finding repeating patterns or wraparound effects to know for sure. And if the topology scale is larger than the observable universe, we might never know. This uncertainty about topology is just one example of a broader theme. There are fundamental limits to what we can learn about the universe from observations. No matter how good our telescopes become, no matter how sophisticated our theories, there will always be questions about the universe that we simply cannot answer from our vantage point within it. The edge of the universe is not just a physical boundary. It's also an epistemic boundary, a limit to knowledge itself. Beyond the horizons of space and time lie questions that might be forever beyond our ability to answer, truths that remain forever hidden behind the veil of causality and light. Chapter 5. The Event Horizon of Existence. There's a particular poignancy to the cosmic event horizon, that boundary beyond which events occurring now can never send us information. It represents not just what we can't currently see, but what we can never see, no matter how long we wait or how advanced we become. It's a final, absolute limit. To understand why this horizon exists, we need to think about the race between light and expanding space. When a photon of light travels through space, it's moving at the speed of light, 300,000 kilometers per second. Nothing can move faster. But space itself can expand faster than light because space isn't moving through anything. It's creating more of itself. In regions sufficiently far from us, the expansion of space is adding distance between us and them faster than light can traverse that distance. It's like a runner on a treadmill, where the treadmill is speeding up. No matter how fast the runner goes, If the treadmill accelerates past a certain point, the runner will never make progress toward the front of the treadmill. The cosmic event horizon, currently about 16 billion light-years away in terms of co-moving distance, marks the boundary where the expansion of space equals the speed of light. Photons emitted from beyond this distance, heading toward us, are actually losing ground. Space is being created between us and them faster than they can traverse it. They're like swimmers trying to swim upstream in a current that's faster than they can swim. They make no progress and are actually carried backward. As dark energy continues to drive the acceleration of expansion, this boundary will remain roughly constant in co-moving coordinates, but the galaxies within it will become fewer and fewer as they're carried across the horizon. Each galaxy that crosses this boundary is lost to us forever, winked out of existence as far as any future observation is concerned. Think about what this means on a human level. Right now, there are galaxies visible in our telescopes that are approaching this boundary. Astronomers are observing them, studying their stars, measuring their properties, but in the far future, those same galaxies will have faded from view, their light stretched by the expansion of space to wavelengths so long that no conceivable detector could find them. Future astronomers will look at the records of their predecessors and see observations of galaxies that no longer appear in the sky. Eventually, in about 150 billion years, assuming the acceleration of expansion continues at its current rate, only the galaxies in our local group will remain visible. The Milky Way, Andromeda, and a few dozen smaller galaxies will be all that future astronomers can observe. Every other galaxy will have receded beyond the cosmic event horizon, vanished from the observable universe. Those future astronomers will live in a very different cosmos from ours. They'll see a universe that appears static, empty, and eternal. There will be no distant galaxies, no redshift to indicate expansion, no cosmic microwave background to point to a hot early universe. If they develop cosmological theories, they might conclude that the universe is infinite and unchanging, occupied only by their local group of galaxies floating in an endless void. They'll be wrong, of course. The universe will still be much larger than what they can see, still expanding, still filled with trillions of other galaxies, but those galaxies will be forever beyond their reach, invisible and unknowable. The evidence for the Big Bang, for cosmic expansion, for dark energy, all of it will have faded beyond detection. This raises a disturbing possibility. Might we be in a similar situation right now? Are there features of the universe, evidence of its true nature, that have already slipped beyond our cosmic event horizon, that existed but can no longer be observed? Have we already lost information about the cosmos that earlier civilizations, if they had existed, might have been able to detect? The answer is yes, almost certainly. The early universe was smaller and denser, and the event horizon has been shrinking in terms of which regions remain observable. There are undoubtedly features of the very early cosmos, processes and structures that formed in the first fractions of a second after the Big Bang, that are now forever beyond our ability to observe because the regions where they occurred are outside our event horizon. This is one of the humbling lessons of cosmology. Not only is the universe larger than what we can see, but it's actively hiding itself from us, pulling more and more of its contents behind an impenetrable veil. The cosmic event horizon is moving through space, encountering galaxies and swallowing them up, removing them from the list of things we can ever know about. And this process is irreversible. A galaxy that crosses the event horizon is gone forever. There's no way to retrieve it, no way to observe it again, no matter what technology we develop. It's not a matter of building bigger telescopes or waiting longer. The information is simply no longer available to us, erased from our accessible universe by the expansion of space-time. This creates a profound sense of urgency in cosmology. Every year that passes, more galaxies slip beyond our reach. Every decade, more of the universe becomes forever unknowable. If we want to understand the cosmos as fully as possible, if we want to observe as many galaxies and structures as we can, we need to do it now, on cosmic timescales. Waiting too long means losing data that can never be recovered. Of course, now, on cosmic timescales means the next few tens of billions of years, so there's no immediate crisis. But the principle stands. The universe is giving us a finite window of time during which it remains observable, and that window is slowly but inexorably closing. Chapter 6: The Quantum Froth and the Planck Scale. So far, we've been thinking about the edge of the universe in terms of distance and light travel time, in terms of cosmic horizons measured in billions of light years. But there's another kind of edge to consider, one that exists not at the largest scales but at the smallest, the quantum edge where space-time itself might break down into something more fundamental. According to our current understanding, space-time is smooth and continuous. You can divide a meter into centimeters, millimeters, micrometers, and keep going, subdividing space into smaller and smaller increments without limit. But quantum mechanics and general relativity suggest that this can't continue forever. At some point, space and time themselves might become granular, quantized, made up of discrete units rather than being infinitely divisible. This scale is called the Planck length, and it's incredibly small, about 10 to the power of minus 35 meters. That's a decimal point followed by 34 zeros, and then a 1. To give you a sense of scale, the Planck length compared to an atom is like an atom compared to the entire solar system. It's the scale at which quantum effects of gravity become important, where space-time itself begins to fluctuate wildly due to quantum uncertainty. At the Planck scale, the smooth fabric of space-time that we experience might give way to a seething foam of quantum fluctuations. Virtual black holes might constantly form and evaporate. The very concepts of distance and time might become fuzzy and ill-defined. This is the regime where we need a theory of quantum gravity to describe what's happening, and unfortunately, we don't yet have a complete, verified theory of quantum gravity. String theory, one of the leading candidates, suggests that at the Planck scale, the fundamental constituents of reality are not particles but tiny vibrating strings of energy. The different vibrational modes of these strings correspond to different particles: electrons, quarks, photons, and so on. In string theory, space might have more than 3 dimensions, perhaps 10 or 11, with the extra dimensions curled up so small that we don't notice them. Loop quantum gravity, another approach, suggests that space itself is quantized, made up of discrete loops of space-time. In this picture, there's a smallest possible area and a smallest possible volume determined by the Planck scale. Space is not infinitely divisible. It's made of fundamental units, like pixels on a screen. These theories remain speculative, and we have no experimental way to probe the Planck scale directly. The energies required are far beyond anything we can achieve with particle accelerators. But there might be indirect evidence. If space is quantized, high-energy gamma-ray photons traveling across billions of light-years might be slightly delayed compared to lower-energy photons, a tiny effect that accumulates over cosmic distances. Some researchers have claimed to see hints of such effects in observations of distant gamma-ray bursts, but the results are controversial and not widely accepted. For now, the Planck scale remains at the edge of our understanding, a theoretical boundary where known physics breaks down and new, unknown physics must take over. But here's an intriguing thought. At the Planck scale, the distinction between the very large and the very small might blur. Some theories suggest that if you could probe distances smaller than the Planck length, you'd find that you're actually probing larger distances, as if space wrapped back on itself at the quantum level. The universe might have not just a maximum scale, the cosmic horizon, but also a minimum scale, the Planck length, with nothing physically meaningful existing beyond either boundary. In a sense, the Planck length represents an edge of the universe in the opposite direction from the cosmic horizon. It's a boundary of smallness rather than largeness, a limit to how finely we can divide reality. And just as we can never see beyond the cosmic horizon no matter how powerful our telescopes, we can never probe below the Planck scale no matter how energetic our experiments. Both boundaries define the limits of the observable and the knowable. Between them, spanning scales from 10 to the power of minus 35 meters to 10 to the power of 26 meters, 61 orders of magnitude, lies the entire accessible universe, everything we can hope to measure, everything we can meaningfully talk about. Beyond those boundaries, in both directions, lies mystery. Chapter 7. The Holographic Boundary. There's another profound idea about the edge of the universe that comes from theoretical physics, one that seems almost too strange to be true, yet is taken seriously by many leading physicists. It's called the holographic principle, and it suggests that in a deep sense, the universe might not be what it seems. Here's the basic idea. You're familiar with holograms, those three-dimensional images encoded on a two-dimensional surface. When you look at a hologram, you see depth, perspective, all the information of a three-dimensional scene, but it's all stored on a flat piece of film. The holographic principle suggests that our entire universe might work the same way. According to this principle, all the information contained in a three-dimensional volume of space can be encoded on the two-dimensional boundary of that volume. It's as if our three-dimensional reality is actually a hologram projected from information stored on a distant two-dimensional surface. This idea emerged from the study of black holes. In the 1970 seconds, physicists Jacob Bekenstein and Stephen Hawking discovered that black holes have entropy, a measure of disorder or hidden information. Surprisingly, the entropy of a black hole is proportional not to its volume but to the area of its event horizon. A black hole twice as large in radius has 4 times the surface area and 4 times the entropy, not 8 times as you'd expect if entropy were related to volume. This suggested something profound. The maximum amount of information that can be contained in a region of space is proportional to the area of the region's boundary, not its volume. It's as if reality is fundamentally two-dimensional, and our experience of 3 dimensions is somehow emergent or illusory. Physicists Gerard Hooft and Leonard Susskind formalized this idea into the holographic principle. In its strongest form, the principle states that our entire observable universe, with all its three-dimensional complexity, all its galaxies and stars and planets, all its history spanning billions of years, could be completely described by information encoded on the two-dimensional cosmic horizon that surrounds us. Think about what this means. You, reading these words, feel like a three-dimensional being moving through three-dimensional space and one-dimensional time. But according to the holographic principle, you might actually be a pattern of information encoded on a distant two-dimensional surface, with your experience of three-dimensionality being an elaborate illusion like the three-dimensional scenes you see in a hologram. This isn't just abstract philosophy. The holographic principle has led to concrete calculations and predictions in physics. In particular, it's been crucial in developing the ADS-CFT correspondence, a mathematical relationship between certain quantum field theories and theories of gravity. This correspondence has allowed physicists to solve difficult problems in quantum chromodynamics and other areas by translating them into simpler problems in gravitational theory. But the holographic principle raises deep questions about the nature of the cosmic boundary. If our universe is holographic, where is the boundary that encodes all the information? Is it the cosmic event horizon? Is it some other surface? And what exists beyond that boundary? One possibility is that the boundary is indeed the cosmic event horizon, the edge beyond which information can never reach us. In that case, the true universe might be a two-dimensional quantum field theory living on this horizon, and our three-dimensional experience is a holographic projection of that more fundamental reality. Another possibility comes from string theory, particularly the ADS-CFT correspondence. In this framework, a universe with a certain kind of curved spacetime called anti-de Sitter space is equivalent to a quantum field theory living on the boundary of that space. Our actual universe doesn't have anti-de Sitter geometry, it has what's called de Sitter geometry due to dark energy. But physicists are working to extend holographic ideas to de Sitter space as well. If our universe is holographic, it raises the question, what's on the other side of the hologram? If we're living in a three-dimensional projection from a two-dimensional surface, is there anything beyond that surface? Or is the surface all there is, with our three-dimensional reality being derived from it? These questions push at the very limits of what we can meaningfully ask about reality. The holographic principle suggests that the edge of the universe might not be a place at all, but rather a fundamental boundary of description, a surface on which the ultimate laws of physics are written. Everything we experience, everything we observe, would be consequences of the information and dynamics on that surface. It's a dizzying idea, one that challenges our most basic intuitions about space, reality, and existence. But it's also a beautiful idea, suggesting deep hidden simplicities underlying the apparent complexity of the cosmos. If the holographic principle is correct, then the universe is in some sense simpler than it appears, its vast three-dimensional expanse encoded in a more fundamental two-dimensional description. And this connects back to the question of what lies beyond the edge. If the edge is not a place but a boundary of description, then asking what's beyond it might be like asking what's north of the North Pole. It's not that there's something there that we can't access. It's that the question doesn't have meaning in the way we think it does. The edge of the universe might be the edge of reality itself, not a boundary in space but a boundary of what can meaningfully be said to exist. Chapter 8. The Dark Energy Mystery. To understand what lies beyond the edge of the universe and what the ultimate fate of that edge might be, we need to confront one of the deepest mysteries in cosmology: dark energy. This mysterious component of the universe is driving its accelerating expansion, pushing the cosmic event horizon farther from us and determining what we'll ever be able to see or reach. We discovered dark energy almost by accident. In the late 1990 seconds, two teams of astronomers were studying distant supernovae, stellar explosions, so bright they can be seen across billions of light years. These particular supernovae, called Type Ia supernovae, all have roughly the same intrinsic brightness, which makes them excellent standard candles for measuring cosmic distances. The astronomers were trying to measure how much the expansion of the universe was slowing down due to gravity. Everyone expected to find that expansion was decelerating. The question was just how quickly. But when they analyzed their data, they found something completely unexpected. The expansion wasn't slowing down at all, it was speeding up. This discovery was so shocking that both teams checked and rechecked their data, looking for errors. But the result held up. The universe's expansion is accelerating, and has been for the past few billion years. The team's leaders, Saul Perlmutter, Brian Schmidt, and Adam Rees, were awarded the 2011 Nobel Prize in Physics for this revolutionary discovery. To explain this acceleration, cosmologists introduced the concept of dark energy. This isn't a specific thing, but rather a name for whatever is causing the acceleration. It could be a property of space itself, a new kind of field permeating the cosmos, or something we haven't even imagined yet. The simplest explanation for dark energy is that it's vacuum energy, also called the cosmological constant. In quantum field theory, even empty space isn't truly empty. It's filled with quantum fields whose ground states have energy. This vacuum energy would have negative pressure, and according to general relativity, negative pressure causes gravitational repulsion rather than attraction. Einstein actually introduced the cosmological constant in 1917, before we knew the universe was expanding, to keep the universe static. When Hubble discovered cosmic expansion, Einstein reportedly called the cosmological constant his biggest blunder and removed it from his equations. But now it seems he might have been right all along, just for the wrong reasons. The cosmological constant appears to be real, and it's the dominant component of the universe's energy budget. However, there's a huge problem. When physicists try to calculate the vacuum energy from quantum field theory, they get an answer that's wrong by a factor of 10 to the power of 120. That's not a typo. Theory predicts a vacuum energy 120 times larger than what we observe. This is the worst prediction in the history of physics, sometimes called the cosmological constant problem. Why is the vacuum energy so much smaller than theory predicts? We don't know. There might be some mechanism that cancels out most of the vacuum energy, leaving just the tiny amount we observe. Or our understanding of quantum field theory in curved space-time might be wrong. Or the answer might involve quantum gravity in ways we don't yet understand. This uncertainty about dark energy's nature has profound implications for the future of the universe and the cosmic event horizon. If dark energy is truly a cosmological constant, a fixed property of space that doesn't change with time, then its effects will continue forever. The universe will expand faster and faster, the cosmic event horizon will remain roughly where it is, and more galaxies will slip beyond it until, in the far future, we're left alone with our local group. But dark energy might not be constant. It could be a field that changes with time, sometimes called quintessence. If this field is slowly decaying, dark energy might weaken in the future, slowing the acceleration. In that case, more of the universe might remain accessible to us than we currently think. Alternatively, dark energy could strengthen over time. If it increases without bound, we could face a scenario called the Big Rip. In this scenario, dark energy becomes so strong that it eventually overwhelms all other forces, even the forces that hold atoms together. The fabric of space would expand so rapidly that molecules, atoms, and even atomic nuclei would be torn apart. The universe would literally rip itself to shreds, and the end would come not in the infinite future, but in a finite time, perhaps 20 billion years from now. Or dark energy could be something called phantom energy, which could lead to even stranger scenarios. Some models predict a big slurp, where the accelerating expansion creates bubbles of different vacuum states that consume our universe. Others predict a big bounce, where the expansion reverses and the universe contracts back to a new beginning. We simply don't know which of these scenarios is correct because we don't understand dark energy. It makes up about 68% of the universe's total energy, dominating the cosmos's evolution. Yet we have almost no idea what it actually is. It's perhaps the greatest mystery in physics. Current and future observations are trying to constrain dark energy's properties. Satellites like the European Space Agency's Euclid and NASA's Nancy Grace Roman Space Telescope will map the distribution of galaxies and measure the expansion history of the universe with unprecedented precision. These observations might reveal whether dark energy is constant or changing, giving us clues about its nature. But until we understand dark energy, we can't fully answer questions about the edge of the universe. We don't know if the cosmic event horizon will remain stable, expand, shrink, or eventually disappear entirely. We don't know if the observable universe will continue to shrink as galaxies recede beyond the horizon, or if this process might somehow reverse. The ultimate fate of the cosmic edge depends on the nature of the most mysterious component of the cosmos. Chapter 9: The Multiverse and the Landscape of Reality. Let's return to the multiverse, because this idea represents perhaps the most radical answer to the question, what lies beyond the edge? If eternal inflation and the string theory landscape are correct, then beyond our observable universe, beyond even our bubble universe, lies an infinite sea of other universes, each with potentially different laws of physics. The string theory landscape emerged from attempts to find a unique theory of everything that would explain all the fundamental forces and particles. String theory seemed promising because it unified quantum mechanics and gravity, something that had eluded physicists for decades. But as researchers explored string theory more deeply, they discovered a problem. The theory didn't predict a single unique set of physical laws. Instead, it predicted something like 10 to the power of 500 different possible vacuum states, each corresponding to different laws of physics. In most versions of physics, a vacuum is the lowest energy state, the state where nothing is happening. But in quantum field theory and string theory, there can be multiple vacuum states, like multiple valleys in a landscape of energy. Which valley you're in determines the laws of physics you experience, the masses of particles, the strengths of forces, even the number of observable dimensions. At first, physicists hoped to find some principle that would select one vacuum state as special, the true vacuum, corresponding to our universe. But no such principle emerged. The landscape seemed to offer an almost infinite menu of possibilities with no way to choose among them. Enter eternal inflation. If inflation is eternal, producing an infinite number of bubble universes, and if each bubble can settle into a different vacuum state from the landscape, then all possible vacuum states would be realized somewhere in the greater multiverse. Our universe would be just one bubble where the physical laws happen to be suitable for our existence. This has profound implications. Many physicists have long wondered why the physical constants of our universe seem fine-tuned for life. Change the strength of gravity by a tiny amount, and stars couldn't form. Change the mass of the electron slightly, and chemistry wouldn't work. Change the cosmological constant by much, and galaxies would never have formed. Why are all these constants balanced just right? In a multiverse, the answer is simple. They're not fine-tuned. Most universes have random values for these constants and are lifeless, sterile places where nothing interesting happens. We live in one of the rare universes where the constants allow for complexity, chemistry, and life, simply because those are the only universes where beings like us could evolve to ask the question. This is the anthropic principle applied to the multiverse. It's not that the universe was designed for us, it's that we naturally find ourselves in one of the universes capable of supporting us, just as fish naturally find themselves in water rather than on dry land. But this raises troubling questions. If every possible universe exists somewhere in the multiverse, does science lose its predictive power? If anything that can happen does happen somewhere, how do we explain why we observe what we observe rather than something else? Physicists have tried to develop a framework for making predictions in the multiverse using what's called the principle of mediocrity. This principle says that, all else being equal, we should expect to be typical observers in a typical universe. If we can calculate how common different types of observers are across the multiverse, we can predict what typical observers should see. But this gets complicated quickly. How do you count observers in an infinite multiverse? If there are infinitely many observers like you, and infinitely many observers different from you, which is more common? Mathematicians call this the measure problem, and it's proven extremely difficult to solve. Some physicists argue that the multiverse is unscientific because we can never observe other universes, and science should be based on observable phenomena. Others counter that the multiverse is a prediction of our best theories, inflation and string theory, and we should take our theories seriously even when they predict unobservable things. The debate continues, but the multiverse idea has become increasingly mainstream in cosmology. It appears in the mathematics of our best theories, and many physicists believe it's the most natural explanation for features of our universe that otherwise seem mysteriously fine-tuned. If the multiverse is real, then the edge of our universe is not an edge at all, but a boundary between our bubble and the eternally inflating space beyond, which in turn contains infinitely many other bubbles. The ultimate reality would be this infinite sea of inflation, constantly spawning new universes, with each universe having its own Big Bang, its own physics, its own destiny. And beyond that, the multiverse itself might be just one possibility among others. Some theories suggest there could be multiple types of multiverses. The quilted multiverse of an infinite space with repeating patterns, the inflationary multiverse of eternal inflation, the quantum multiverse of many worlds, quantum mechanics, and even a mathematical multiverse where every mathematically consistent structure exists as a physical reality. In this ultimate vision, the question, what lies beyond the edge, has a dizzying answer. Everything that could possibly exist does exist. Every universe that's mathematically possible is physically real somewhere, somewhen, somehow. Our universe, our entire multiverse, our very concept of physical reality would be just one tiny corner of a vast mathematical landscape of all possible worlds. Chapter 10. The Quantum Multiverse. There's another type of multiverse that deserves attention, one that comes not from cosmology but from quantum mechanics itself, the many worlds interpretation. This idea suggests that every time a quantum measurement occurs, the universe splits into multiple copies, one for each possible outcome. If this is correct, then the edge of reality extends not just through space, but through an infinite branching of quantum possibilities. Quantum mechanics is famously weird. When you're not observing a quantum particle, it exists in a superposition of multiple states simultaneously. An electron can be in many places at once, or spinning in multiple directions. But when you measure the electron, you always find it in one definite state. The act of measurement seems to collapse the superposition into a single outcome. This raises the measurement problem. What counts as a measurement? Why does observation affect reality? What determines which outcome you see when you measure a superposition? The standard interpretation, called the Copenhagen interpretation, says that the wave function describing the superposition genuinely collapses when measured, selecting one outcome randomly according to quantum probabilities. But this raises more questions than it answers. What causes the collapse? How does nature choose which outcome to select? In 1957, physicist Hugh Everett proposed a radical alternative. There is no collapse. When you measure a quantum superposition, all possible outcomes occur, but they occur in different branches of reality. The universe splits into multiple copies, one for each outcome, and you find yourself in one of those branches, while other versions of you experience the other outcomes in other branches. This is the many worlds interpretation of quantum mechanics. It sounds like science fiction, but it's taken seriously by many physicists because it solves the measurement problem without invoking mysterious collapse mechanisms or special roles for consciousness. In the many worlds picture, every quantum event causes the universe to branch, and quantum events are happening constantly, everywhere, trillions upon trillions of them every second. Each time an atom emits or absorbs a photon, the universe branches. Each time particles interact, more branches are created. The total number of branches grows exponentially, doubling every tiny fraction of a second. This creates a multiverse of staggering proportions, far larger than the inflationary multiverse. Instead of 10 to the power of 500 or so bubble universes, the many worlds multiverse contains an uncountably infinite number of branches, one for every possible history of quantum events. In this multiverse, there are countless versions of you. In some branches, you made slightly different choices moments ago. In others, you look different because your DNA developed slightly differently in the womb due to quantum randomness. In others still, you never existed because some crucial quantum event went differently billions of years ago. But here's the thing, you can never observe or interact with these other branches. The branching is one way and irreversible. Once histories split, they never rejoin. Each branch is causally disconnected from all the others, evolving independently according to the laws of physics. So in what sense do these other branches exist? They don't exist in our space-time, in the universe we can observe. They exist in a larger structure called the wave function of the universe or configuration space, a mathematical object that encompasses all possible quantum states. This raises deep philosophical questions. If we can never observe these other branches, if they have no effect on our branch, do they exist in any meaningful sense? Or are they just mathematical abstractions, useful for calculations but not physically real? Proponents of many worlds argue that the other branches are just as real as our own. The fact that we can't access them doesn't make them less real, any more than distant galaxies beyond our cosmic horizon are less real because we can't see them. The wave function of the universe is the fundamental reality, and our perception of a single classical world is just our limited view of one branch. Critics argue that this multiplies entities beyond necessity. If we can explain all observations without invoking unobservable parallel worlds, why believe in them? The debate has continued for decades with no clear resolution. But if many worlds is correct, it provides another answer to what lies beyond the edge. Beyond the boundary of our branch of the quantum multiverse lie all the other branches, all the other possible histories, all the other versions of you and me, and everything else. These branches don't lie beyond us in space. They're separated from us in the abstract space of quantum possibilities. The edge here is not a boundary in physical space, but a boundary in probability space, the line dividing what happened in our branch from what happened in others. And this boundary is constantly moving, constantly shifting, as new quantum events occur and new branches split off. Interestingly, some physicists have tried to combine the many worlds interpretation with the cosmological multiverse. Perhaps each bubble universe in the inflationary multiverse itself branches according to quantum mechanics, creating a multiverse of multiverses. Or perhaps the many worlds, branches, and the cosmological bubbles are really the same thing, different ways of describing the same underlying structure. These ideas push at the absolute limits of theoretical physics, venturing into territory where mathematics, philosophy, and speculation blend together. But they represent serious attempts by serious scientists to understand the deepest structure of reality, to answer the question of what, if anything, lies beyond the edges of our observable universe. Chapter 11. The Simulation Hypothesis. There's one more possibility we should consider, one that sounds like pure science fiction but has been seriously discussed by philosophers and physicists. Perhaps we live in a computer simulation and the edge of our universe is simply the boundary of the simulated region. The argument goes like this. Suppose it's possible, in principle, for a sufficiently advanced civilization to create detailed computer simulations of universes with conscious beings inside them. We're already creating increasingly sophisticated simulations and virtual worlds, so this doesn't seem impossible, just technologically difficult. Now, if it's possible to create such simulations, and if civilizations advanced enough to create them are even moderately common, then there should be vastly more simulated universes than real ones. After all, one advanced civilization could run millions or billions of simulations. If you accept these premises, then purely statistically, you're more likely to be living in a simulation than in the base reality. This is the simulation argument, most famously articulated by philosopher Nick Bostrom. If we are in a simulation, what would the edge of the universe be? It would be the limits of what the simulators chose to simulate. Perhaps they're only simulating our local region of space, and everything beyond is just a kind of cosmic background, less detailed or even not computed until we look at it. This would explain some puzzling features of physics. Quantum mechanics, with its probabilistic nature and the way that observation affects reality, could be understood as computational shortcuts. The simulator doesn't need to compute the exact state of every particle at all times. They can leave things in superposition until someone observes them, then compute the result. The speed of light could be understood as the frame rate of the simulation, the fastest speed at which information can propagate through the simulated universe. The Planck length could be the pixel size of the simulation, the smallest meaningful scale. The apparent fine-tuning of physical constants could be explained if the simulators deliberately chose parameters that would lead to interesting complexity, just as game designers balance game parameters to make their games fun and interesting. Of course, this raises the question, if we're in a simulation, who's simulating us? And are they in a simulation too? Perhaps there's an infinite regress of simulations within simulations. Or perhaps there's a base reality somewhere, and we're a few layers deep in nested simulations. Some physicists have proposed tests for the simulation hypothesis. If we're in a simulation, there might be glitches or artifacts, patterns in the data that reveal the underlying computational structure. They've looked for things like asymmetries in the cosmic microwave background or unexpected correlations in high-energy cosmic ray data. So far, no smoking gun has been found. But that doesn't mean we're not in a simulation. It just means that if we are, it's a very good one, with no obvious errors or shortcuts. Most physicists are skeptical of the simulation hypothesis, not because it's logically impossible, but because it doesn't really explain anything. If we're in a simulation, we still need to understand the laws of physics as they apply within the simulation. And the base reality, where the simulator exists, presumably has its own laws of physics that need explaining. We've just pushed the mystery up one level. Moreover, the simulation hypothesis isn't really testable in a meaningful way. If we found evidence that we're in a simulation, we could never be sure it wasn't itself part of the simulation, a deliberate clue placed by the simulators. And if we don't find evidence, that doesn't prove we're not in a simulation. It might just mean the simulation is well designed. Still, the idea provides an interesting perspective on the question of what lies beyond the edge. If we're simulated, the edge might be a computational boundary, the limit of what resources the simulators allocated to modeling our region of space. Beyond that edge might simply be null data, regions that haven't been computed because there's no need to. Or perhaps the edge is permeable from the outside. Maybe advanced simulated beings could, in principle, hack their way through the boundary, gaining access to the computational substrate on which they're running, potentially even communicating with the simulators or other simulated universes. These ideas verge on metaphysics more than physics, but they're worth considering as we explore all possible answers to what lies beyond our observable universe. The truth is, we don't know what's out there, and some possibilities are stranger than others. Chapter 12: The Philosophy of Unknowable Truths. As we've explored various ideas about what might lie beyond the edge of the universe, we've repeatedly encountered a common theme: limits to knowledge. There are questions we can't currently answer, questions we might never be able to answer, and questions that might not even have answers in any meaningful sense. This confronts us with deep philosophical issues. What does it mean to say something exists if it's impossible in principle to observe it? What's the difference between a truth we can't know and something that isn't true at all? Consider the region of space beyond our cosmic event horizon. We've said that light from events happening there now will never reach us. But does that mean those events don't exist? Most physicists would say no. The events are real, we just can't observe them. The universe beyond the horizon is just as real as the universe within it. But how do we know this? We've never observed anything beyond the horizon and never will. Our belief that there's more universe out there is based on theoretical extrapolation, on the assumption that the laws of physics we observe locally continue to apply in regions we can't see. This assumption seems reasonable, but it's still an assumption. Maybe the universe really does end at our cosmic horizon. Maybe there's nothing beyond it, and light from beyond doesn't reach us because there is no beyond. How would we tell the difference? Philosophers call this problem the problem of unverifiables. How do we deal with claims that can't be verified, even in principle? Traditional scientific methodology says we should be skeptical of such claims, that we should only believe things we can test. But modern cosmology seems to force us to think about unverifiable things, regions beyond the horizon, other universes in the multiverse, quantum branches we can never observe. Some philosophers and scientists argue that we should apply Occam's razor, prefer the simplest explanation that fits the observed data. The simplest cosmological models that explain what we observe also predict vast regions beyond the horizon, so we should tentatively accept that those regions exist, even though we can't verify it. Others argue that we need a principle of mediocrity or Copernican principle. Assume we're not special, that our location in space and time is typical. If we can see part of the universe, and that part follows certain laws and has certain properties, we should assume the parts we can't see are similar unless we have reason to think otherwise. Still, others suggest we need to be more radical and accept that science can and should make claims about unobservables if those claims are part of our best theories. Electrons and quarks are, in a sense, unobservable. We only see their effects, but they're essential parts of our best theories of matter, so we believe in them. Perhaps other universes in the multiverse are similar, unobservable but theoretically necessary. These debates get at fundamental questions about the nature of scientific knowledge. Is science only about describing observations, or is it about uncovering true reality, even when that reality extends beyond what we can observe? Can we meaningfully distinguish between a theory that says the universe extends infinitely in all directions, and one that says it ends just beyond our horizon, if both theories make the same predictions for everything we can observe? There's also the question of what we mean by real. In everyday language, Real means something that exists independent of our minds, something that would be there whether or not anyone observed it. But quantum mechanics complicates this. In some interpretations, observation plays a fundamental role in determining what's real. Before a measurement, particles don't have definite properties. They exist in superpositions. Only measurement creates definite reality. If this is true, what does it mean for regions of the universe that have never been and will never be observed by anyone? Do they have definite properties? Are they real in the same sense as things we've observed? These questions don't have clear answers. They're still being debated by physicists and philosophers, and they might never be fully resolved. But they're important questions to think about as we contemplate the edge of the universe and what, if anything, lies beyond it. One thing seems clear: the universe is under no obligation to make sense to us. It doesn't have to be comprehensible or fully knowable. The fact that we've learned as much as we have about the cosmos is itself remarkable. Every answer we've found has revealed new questions, and this process seems unlikely to end. The edge of the universe represents, in many ways, the edge of human knowledge. It's where what we know fades into what we can speculate about, and beyond that, into what we might never be able to know. But that doesn't mean we should stop asking questions or exploring ideas. The journey toward understanding is valuable even if we never reach a final destination. Chapter 13: The Ultimate Fate of Everything. Let's turn our attention to the future. What will happen to the edge of the universe as time goes on? What's the ultimate fate of the cosmos? And how does that fate affect what exists beyond our horizon? Based on current observations and our understanding of dark energy, the most likely scenario is called the Big Freeze or heat death. In this scenario, the universe continues expanding forever, accelerating due to dark energy. Galaxies move farther and farther apart, eventually receding beyond each other's cosmic event horizons. Over the next 100 billion years, the night sky will darken as more and more galaxies vanish from view. In 1 trillion years, the only galaxies remaining visible from the Milky Way will be those in our local group. In 10 trillion years, star formation will have ended everywhere as galaxies exhaust their supplies of hydrogen gas. The universe will be filled with aging and dying stars, white dwarfs, neutron stars, and black holes. In 10 to the power of 14 years, 100 trillion years, the last stars will burn out. The universe will go dark, lit only by the occasional flare as material falls into black holes or as brown dwarfs collide. But things don't stop there. Over vastly longer timescales, even seemingly permanent structures will decay. Planets will be ejected from their solar systems through gravitational interactions. Stars will be ejected from galaxies. On timescales of 10 to the power of 30 years, galaxies themselves will evaporate, their stars scattered into intergalactic space. On even longer timescales, matter itself might decay. Some theories predict that protons aren't stable but will eventually decay into lighter particles. The current lower bound on proton lifetime is about 10 to the power of 34 years, but if protons do decay, even that will eventually happen. By 10 to the power of 40 years, all ordinary matter might have decayed, leaving only black holes as the dominant structures in the universe, and even black holes won't last forever. Stephen Hawking showed that black holes emit radiation due to quantum effects, slowly evaporating over time. A solar mass black hole will evaporate in about 10 to the power of 67 years. Supermassive black holes will last longer, but even they will eventually disappear. The largest black holes, those containing trillions of solar masses, will evaporate in about 10 to the power of 100 years. After that, the universe will contain nothing but a dilute gas of photons and fundamental particles spread thinner and thinner as space continues to expand. The temperature will approach absolute zero. This is the heat death, maximum entropy, maximum disorder, everything in equilibrium with nothing interesting happening anymore. But wait, there's more. Even in a universe of maximum entropy, quantum mechanics allows for random fluctuations. Very rarely, purely by chance, particles might spontaneously arrange themselves into something complex. These are called Boltzmann brains, named after physicist Ludwig Boltzmann, who first explored these ideas. A Boltzmann brain is a self-aware observer that arises spontaneously from random fluctuations, complete with false memories of a history that never happened. In the infinite future of an eternally expanding universe, such fluctuations, while extraordinarily rare, will eventually occur. In fact, in an infinite future, they'll occur infinitely many times. This raises a disturbing possibility. If the universe lasts forever and produces infinite Boltzmann brains, then by pure statistics, you're more likely to be a Boltzmann brain with false memories than an actual observer with a real history. This is called the Boltzmann brain problem, and it's a serious issue for cosmological models with infinite futures. Some cosmologists argue that this problem indicates that our current understanding is incomplete, that something must prevent the universe from entering this state of eternal random fluctuations. Maybe the universe doesn't last forever after all. Maybe vacuum decay will occur, where our current vacuum state is only metastable and will eventually quantum tunnel to a true lower energy vacuum, destroying our universe and creating something new. Or maybe dark energy will strengthen over time, leading to a big rip where the fabric of space expands so rapidly that it tears apart all structures, even atoms, in a finite time. Or maybe dark energy will decay, slowing the expansion, potentially even reversing it, and leading to a big crunch where the universe collapses back to a singularity. We don't know which of these scenarios will actually occur because we don't understand dark energy. The ultimate fate of the universe remains one of the greatest open questions in cosmology. But whatever happens to our universe, what about the regions beyond our cosmic horizon? In a big freeze scenario, they'll continue to exist forever beyond our reach, slowly fading as they too exhaust their stars and enter heat death. In a big rip, they'll be torn apart just as we are, though we'll never see it happen. In a big crunch, they'll collapse along with us, though different regions will collapse at different times. And if we're part of a multiverse, what happens to other universes? They'll each have their own fates, determined by their own dark energy and physical constants. Some might already have ended in big rips or big crunches. Others might be just beginning, and the eternally inflating space between bubbles will continue forever, constantly spawning new universes. In this picture, individual universes come and go, but the multiverse itself is eternal. There's no ultimate end, just an endless cycle of creation and destruction, universes being born and dying in an infinite sea of possibilities. The edge of our universe might disappear in heat death or a big rip, but countless other edges are forming elsewhere as new bubble universes emerge from eternal inflation. This provides a strange kind of comfort. Even if our universe ends, even if everything we know fades into darkness or tears itself apart, reality itself continues. The story doesn't end with us. New chapters are constantly being written in other corners of the multiverse, new possibilities being explored, new structures forming and evolving. Of course, this assumes the multiverse is real, which remains controversial, but whether or not there are other universes, the far future of our own universe raises profound questions about meaning and purpose. If everything is destined to decay into a cold, dark, empty state, does anything we do matter? Does the universe have any ultimate purpose or direction? These are not scientific questions in the strict sense. Science can tell us what will happen, but not whether it matters. That's a question for philosophy, for individual reflection, for each person to answer in their own way. But there's something remarkable to consider. Right now, in this brief cosmic moment, the universe is in a special state. Stars are shining, galaxies are forming structures, life has emerged, consciousness has evolved. We exist in what might be called the universe's age of stars and life, a relatively brief period between the hot early universe and the cold late universe, when interesting things can happen. In the vast sweep of cosmic time, from the Big Bang to the heat death, this period occupies a tiny sliver, perhaps a trillionth of the universe's total lifetime. And we're here, now, able to observe and understand it. That's either a remarkable coincidence or an inevitable consequence of the fact that observers can only exist during such special times. The edge of the universe, then, is also temporal. We live not just at a particular location in space, but at a particular moment in time, bounded by horizons in both space and time. Behind us lies the Big Bang, the moment of creation that we can probe but never directly observe. Ahead lies the far future, which we can predict but never experience. We're confined to a bubble in space-time, limited in both spatial extent and temporal duration. But within that bubble, within this brief cosmic moment when stars shine and life flourishes, we have the extraordinary privilege of being able to wonder, to question, to seek understanding. The universe has become conscious of itself through us, has developed the ability to contemplate its own existence and fate. That seems like something worth celebrating, regardless of what lies beyond the edges of our knowledge or what ultimate fate awaits in the far future. Chapter 14. The Information Paradox and Cosmic Horizons. There's a deep connection between cosmic horizons and the nature of information that deserves exploration. This connection reveals fundamental limits not just on what we can observe, but on what can be known, even in principle, about the universe beyond our reach. In physics, information is a technical concept related to entropy and the number of possible states a system can be in. The laws of quantum mechanics appear to require that information is conserved. It can be transformed or encoded in different ways, but never truly destroyed. This principle has been tested in countless experiments and seems to be fundamental to how reality works. But cosmic horizons create a problem. When a galaxy crosses our cosmic event horizon and disappears from view, what happens to the information it contains? That galaxy has a particular arrangement of matter, particular histories of events, specific states of all its particles. All of that is information, and now it's gone, forever, beyond our ability to access. Does this violate the principle that information is conserved? Or does information conservation only apply within a single causal region, within our observable universe, but not necessarily across horizon boundaries? This question is closely related to the black hole information paradox that Stephen Hawking discovered in the 1970 seconds. When matter falls into a black hole, it carries information with it. But Hawking showed that black holes evaporate through Hawking radiation, and this radiation appeared to be completely thermal, carrying no information about what fell in. When the black hole finally evaporates completely, the information seems to be lost. This apparent violation of information conservation troubled physicists for decades. It suggested that black holes could destroy information, which would require modifying quantum mechanics in fundamental ways. After much debate and calculation, most physicists now believe that information is not actually lost in black holes. Instead, it's encoded in subtle correlations in the Hawking radiation, or perhaps stored in the quantum structure of the event horizon itself. The resolution of the black hole information paradox might have implications for cosmic horizons. Perhaps information about regions beyond our cosmic horizon isn't truly lost, but is somehow encoded in the structure of the horizon itself, or in subtle correlations in the radiation that crosses it. This connects to the holographic principle we discussed earlier. If the maximum amount of information in a region is proportional to the area of its boundary rather than its volume, then perhaps all the information about regions beyond our horizon is encoded on the horizon itself. The universe beyond would be, in some sense, redundant, its information already present in the holographic description on the boundary. But this raises more questions than it answers. If the information is encoded on the horizon, is the region beyond the horizon real in any meaningful sense? Or is it a kind of holographic projection, with the horizon being the fundamental reality? Different physicists have different views on these questions. Some argue that the region beyond the horizon is real and contains information we simply can't access. Others suggest that asking about regions beyond horizons is meaningless because those regions are fundamentally disconnected from us. Still, others propose that horizons represent boundaries not just of observable reality but of reality itself. There's also the question of what happens to information in different cosmic scenarios. In a big freeze scenario where the universe expands forever, information becomes increasingly dilute but is never destroyed. The total information content of the observable universe might actually decrease as galaxies cross the cosmic event horizon, but that information still exists, just beyond our reach. In a big crunch scenario where the universe collapses, all information would eventually be compressed into a singularity. Would it be preserved through the crunch, potentially seeding a new Big Bang with the information from the previous universe? Or would it be destroyed, requiring new information to be created in the subsequent expansion? In a big rip scenario, the accelerating expansion would eventually tear apart all structures, potentially destroying information in the process. Or would the information survive in some form, perhaps encoded in the quantum structure of space-time itself? These questions push at the boundaries of current physics. We don't have a complete theory of quantum gravity that could definitively answer them, but they're not just abstract puzzles. They're questions about what's fundamentally real, about what exists beyond what we can observe, about the ultimate nature of the cosmos. One intriguing possibility is that information might be the most fundamental thing in the universe, more fundamental even than matter or energy. Some physicists, following ideas originally proposed by John Wheeler with his phrase "it from bit," suggest that reality at its deepest level is informational, and matter and energy are emergent phenomena arising from underlying information structures. If this is true, then the edge of the universe might be better understood as an information boundary than a spatial boundary. The cosmic horizon would mark the limit of informationally accessible reality, and what lies beyond would be information that's disconnected from our informational network, existing in a separate informational domain. This perspective shifts the question from what exists beyond the edge to what information exists beyond the edge, and is it connected to our information in any way? And it suggests that the ultimate structure of reality might be more like a network of information than a container of stuff. Chapter 15: Time's Arrow and the Edge of the Temporal Universe. We've focused primarily on spatial edges, on how far we can see in space, but there are also temporal edges to consider: the beginning of time at the Big Bang and the potential end of time in the far future. These temporal boundaries are just as much edges of the universe as spatial horizons, and they raise equally profound questions. The Big Bang represents the edge of time in the past direction. Current physics breaks down at the moment of the Big Bang itself. Our equations produce infinities and lose predictive power. We can trace the universe's history back to tiny fractions of a second after the Big Bang, but that first moment remains mysterious. What happened before the Big Bang? For decades, the standard answer was that this question is meaningless. If time itself began at the Big Bang, there was no before. Asking what came before time is like asking what's north of the North Pole. The question assumes a framework that doesn't exist, but some modern theories suggest there might have been something before. In certain inflationary models, our Big Bang was just a local event in a pre-existing, eternally inflating space. Time didn't begin with our Big Bang. Rather, our region of space began evolving in a particular way at that moment, while time continued in other regions. In cyclic cosmological models, the universe undergoes repeated cycles of expansion and contraction. Each cycle might end in a big crunch that triggers a new Big Bang, with the process repeating eternally. In this picture, our Big Bang was preceded by the end of a previous cycle, and time extends infinitely into both past and future. In some quantum gravity theories, particularly loop quantum gravity, the Big Bang singularity is replaced by a quantum bounce. The universe might have existed in a contracting phase before reaching a minimum size and then bouncing into the expanding phase we observe. Time would extend through the bounce, connecting a previous contracting universe to our expanding one. These ideas remain speculative, but they suggest that the temporal edge of our universe at the Big Bang might not be absolute. There might be a temporal beyond, a time before our Big Bang, just as there might be a spatial beyond, outside our cosmic horizon. Looking forward in time, we face similar questions. Will time continue forever, or is there an end to time itself? In most cosmological scenarios, time continues indefinitely. The universe might undergo heat death, but time keeps ticking even in a cold, empty cosmos. Clocks might stop working and events might become rare, but time itself doesn't end. However, in a Big Rip scenario, things are different. If dark energy strengthens without bound, the expansion of space accelerates to infinity in finite time. Space itself becomes infinitely large in a finite number of years. What happens to time in this scenario? Some calculations suggest that the Big Rip represents a true end to time, a singularity where not just space, but space-time itself comes to an end. Beyond this point, there would be no time, no possibility of events, no meaningful sense in which anything could exist or happen. Other scenarios involving vacuum decay or transitions between different vacuum states might also represent ends to time, at least for our particular region of space-time. A vacuum decay bubble expanding at the speed of light would destroy everything in its path, including the structure of space-time itself, replacing it with a different vacuum with different properties. There's also the question of the arrow of time, the fact that time seems to flow in one direction. We remember the past, but not the future. Eggs break but don't spontaneously reassemble. Entropy increases. Why? The answer seems to be related to the low entropy state of the early universe. The Big Bang created a universe that was remarkably organized, with matter and energy distributed smoothly and density fluctuations that were tiny. This provided a low entropy starting point from which entropy could increase, creating the arrow of time we experience. But why was the early universe in such a low entropy state? We don't know. Some theories suggest it's related to inflation, which would have smoothed out any initial irregularities. Others propose that the low entropy is just an unlikely initial condition that we happen to find ourselves in because high entropy universes wouldn't produce observers like us. In a multiverse scenario, different universes might have different arrows of time, or some might have no arrow at all. In cyclic cosmologies, the arrow of time might reverse in contracting phases, with entropy decreasing rather than increasing. These considerations about time's nature and its boundaries remind us that the edge of the universe isn't just a spatial concept. We're bounded in time as well as space, able to see back to the Big Bang but no further, and forward to some future horizon beyond which our models become uncertain. The temporal edges of the universe are, in a sense, more absolute than the spatial edges. We can, in principle, travel to any spatial location given enough time and technology, but we can never travel backward in time to before the Big Bang, and if time has an end, we can never see beyond it. These temporal boundaries are final and insurmountable in ways that spatial boundaries might not be. Chapter 16. The Anthropic Edge. There's another kind of edge worth considering: the boundary of conditions compatible with life and observers. This anthropic edge doesn't correspond to a place or time, but to a region in the space of possible physical parameters. Understanding this edge helps us think about why the universe we observe has the properties it does. The observable universe has many properties that seem remarkably fine-tuned for the existence of life. Change any of numerous physical constants by even small amounts, and the universe would be radically different, unable to support life as we know it. For example, if gravity was slightly stronger, stars would burn out too quickly for life to evolve. If it were slightly weaker, stars wouldn't form at all. If the strong nuclear force were a bit different, atoms heavier than hydrogen wouldn't be stable. If the electromagnetic force had a different strength, chemistry wouldn't work. If the cosmological constant were much larger, galaxies would never have formed. This apparent fine-tuning has puzzled physicists for decades. Why do we find ourselves in a universe balanced so precisely for our existence? There are three main types of answers. First, it might be luck. Perhaps there's only one universe, and we just happen to get physical constants compatible with life. The odds might be astronomically small, but somebody has to win the lottery, and we're clearly here, so it must have happened. This answer feels unsatisfying because it seems to require an implausible coincidence. Second, it might be design. Perhaps the universe was intentionally created with these properties by some intelligence or deity. This moves the question outside the realm of science into theology or philosophy, and it doesn't really answer the question so much as push it back a level. Why would a creator choose these particular values? Third, it might be selection. If there are many universes with different physical properties, most randomly determined, then we naturally find ourselves in one of the rare universes compatible with observers. We couldn't exist in universes with different parameters, so of course we observe parameters compatible with our existence. This third answer is the anthropic principle, and it gains explanatory power in the context of a multiverse. If eternal inflation or other mechanisms produce countless universes with varying properties, then the fine-tuning problem dissolves. Most universes are sterile and lifeless, but a few have the right properties for complexity and life. We're in one of those few not because it was specially created or because we got lucky, but because those are the only universes where beings like us could ask the question. The anthropic principle has been controversial. Some physicists embrace it as a natural consequence of multiverse cosmology. Others reject it as giving up on finding deeper explanations for physical constants. Why should we accept that constants are random when we might eventually discover a theory that predicts their exact values? The debate continues, but the anthropic principle raises interesting questions about edges. In the space of possible physical parameters, there's a boundary, an anthropic edge, separating universes that can support observers from those that can't. This edge is multidimensional, defined by numerous conditions that must all be satisfied simultaneously. Within this anthropic edge, there might be regions supporting different types of observers. Perhaps some parameter combinations allow for carbon-based life like us. Others might allow for silicon-based life or exotic chemistry we can't imagine. Some might support life based on electromagnetic forces, others on exotic physics we haven't discovered. The anthropic edge also has a temporal component. Early in any universe's history, before stars have formed and created heavy elements, life probably can't exist regardless of the physical constants. Similarly, in the far future after all stars have died, conditions become inhospitable again. So there's a temporal window, an age of the universe during which observers can exist. We find ourselves in a universe that's about 13.8 billion years old, which seems to be roughly the right age for the anthropic window. Much younger, and there wouldn't have been time for stars to form, live, die, and create the heavy elements necessary for life. Much older, and we'd be approaching the end of the stellar era when star formation is winding down. This temporal anthropic edge might explain why we observe the cosmological constant to have the value it does. If it were much larger, the universe would have expanded so quickly that galaxies never formed. If it were smaller or negative, the universe might have recollapsed before life could evolve. The value we observe is roughly the largest value compatible with galaxy formation, and hence with observers. Some physicists have used this reasoning to predict the approximate value of the cosmological constant before it was measured, a rare example of the anthropic principle making a successful prediction. The anthropic edge reminds us that when we ask about what lies beyond the edge of the universe, we might also ask, beyond what edges could observers exist? Could there be regions of the multiverse so different from ours that entirely alien forms of observation and consciousness exist there? Or is there something special about the conditions we observe, something that makes them not just compatible with life but optimal for it? These questions blur the line between physics and philosophy, but they're worth contemplating. The edge of the observable universe might coincide with an edge of observability itself, a boundary beyond which conditions are so different that observation, consciousness, and awareness, as we understand them, cannot exist. Chapter 17. The Mathematical Edge. Let's consider one final type of edge, the boundary between what can be described mathematically and what cannot. Mathematics is the language of physics, the tool we use to describe the universe and make predictions. But are there aspects of reality that lie beyond mathematical description? All our physical theories are mathematical at their core. General relativity describes gravity using the mathematics of differential geometry. Quantum mechanics uses linear algebra and probability theory. The standard model of particle physics uses group theory and quantum field theory. Even seemingly simple concepts like velocity and acceleration are defined mathematically. This mathematical structure of physics suggests a deep connection between mathematics and reality. Some physicists and philosophers, including Max Tegmark with his mathematical universe hypothesis, have proposed that reality is mathematics, that the universe doesn't just obey mathematical laws but actually is a mathematical structure. In this view, what we call physical existence is really mathematical existence. The universe exists in the same sense that mathematical structures like numbers, sets, and geometries exist. Physical laws aren't rules that matter obeys. They're the relationships inherent in the mathematical structure that constitutes reality. If this is true, then asking what lies beyond the edge of the universe might be equivalent to asking what mathematical structures exist beyond the one we inhabit. And since all consistent mathematical structures exist in some abstract sense, the answer might be everything that can be mathematically described exists somewhere as a physical reality. This is a radical form of multiverse, the mathematical multiverse, or level 4 multiverse in Tegmark's classification. It's more expansive than the inflationary multiverse or the many worlds multiverse, because it includes not just different regions of space or different quantum branches, but entirely different mathematical structures with completely different laws of physics. In one mathematical universe, space might have 3 dimensions and time 1. In another, space might have 5 dimensions. In another, there might be no distinction between space and time at all. Some mathematical universes might obey quantum mechanics. Others might be purely classical. Some might have particles and forces. Others might have entirely different fundamental constituents. Most of these mathematical universes would be incomprehensibly alien to us. But if the mathematical universe hypothesis is correct, they all exist in some sense, and collectively they represent the ultimate multiverse, the set of all possible realities. This raises the question, is there a boundary to mathematics itself? Are there some structures that are too paradoxical or contradictory to exist even mathematically? Most mathematicians would say yes. Mathematical structures must be logically consistent. You can't have a universe where 2 plus 2 equals both 4 and 5. Contradictions mark the boundary of mathematical existence. But beyond that requirement of consistency, mathematics seems almost limitless in its possibilities. There are infinitely many different consistent mathematical structures, and if the mathematical universe hypothesis is correct, they all correspond to real universes in some sense. However, there might be limitations we haven't discovered. Kurt Gödel's incompleteness theorems showed that in any sufficiently complex mathematical system, there are true statements that cannot be proven within that system. Some mathematical truths are forever beyond proof, lying at the edge of what can be known even mathematically. Perhaps reality has similar limitations. Perhaps there are aspects of the universe that are true but cannot be derived from any set of axioms, cannot be predicted by any theory, exist beyond the edge of mathematical describability. Quantum mechanics hints at this. The theory makes probabilistic predictions but cannot predict individual outcomes. An electron will either go through one slit or the other, but quantum mechanics cannot tell you which. Is this just a limitation of our current theory, or is there genuine randomness in nature, events that have no mathematical cause or explanation? If there's genuine randomness, then reality contains an element that transcends mathematical description. Mathematics can describe the probabilities, but not the actual outcomes. The specific universe we inhabit, with all its contingent details, might lie partially beyond the mathematical edge. Some philosophers argue that consciousness represents another aspect of reality that might transcend mathematical description. Subjective experience, qualia, the felt sense of what it's like to be you, can these be captured in equations? Or do they represent something that exists beyond mathematical structure? These are ancient questions in philosophy of mind, and they don't have clear answers. But they suggest that the edge of the universe might also be an edge of describability, a boundary beyond which our mathematical tools fail and reality becomes ineffable. When we ask what lies beyond the edge, perhaps the deepest answer is things that cannot be described, cannot be modeled, cannot be captured in any formal system. Not just things we haven't figured out how to describe yet, but things that are inherently beyond description. This would represent an absolute limit to knowledge, an edge beyond which even the most advanced science and mathematics cannot go. It would be a cosmic version of Gödel's theorem. In any system complex enough to contain us, there are truths about that system that we cannot prove or even properly formulate. The universe might be telling us, through its horizons and boundaries, that there are limits to what minds like ours can know. Not practical limits that might be overcome with better technology, but fundamental limits written into the structure of knowledge itself. Chapter 18. Living at the Edge. After all this exploration of cosmic horizons, multiverses, and the limits of knowledge, let's return to a more human scale. What does it mean for us, as individuals living our brief lives, that we exist at the edge of something unimaginably vast? Every person who has ever lived has existed in the same cosmic situation we find ourselves in now, bounded by horizons in space and time, able to observe only a tiny fraction of reality, uncertain about what lies beyond. Yet this hasn't stopped humans from wondering, exploring, and seeking understanding. In some ways, our situation today is remarkable. For most of human history, people had no idea about the scale of the cosmos. The visible universe, the stars overhead, seemed to encompass everything. Even 100 years ago, many astronomers thought the Milky Way was the entire universe, that nothing existed beyond our galaxy. Now we know better. We know about the 93 billion light-year span of the observable universe. We know about the 2 trillion galaxies it contains, each with hundreds of billions of stars. We understand cosmic expansion, dark energy, and the horizons that limit what we can see. We've developed theories about multiverses and eternal inflation, about the possibility of infinitely many universes beyond our own. This knowledge hasn't diminished the mystery. If anything, it's made the mystery deeper and more profound. The more we learn about the universe, the more we realize how much remains unknown. Each answered question reveals new questions we hadn't thought to ask. But there's something empowering about this knowledge too. We're no longer passive observers wondering about the lights in the sky. We're active investigators with tools and theories that let us probe the deepest secrets of nature. We've measured the expansion rate of the universe, mapped the cosmic microwave background, detected gravitational waves from merging black holes billions of light years away. We live at what might be a unique moment in cosmic history. The universe is old enough that intelligent life has had time to evolve, yet young enough that there's still much to observe. The stars still shine. Galaxies are still visible. The cosmic microwave background still carries information about the early universe. In the far future, as we discussed, much of this will be gone. Future astronomers will see a much emptier cosmos. They'll have lost access to evidence that we can still observe. In this sense, we're privileged. We live during the universe's age of discovery, when the cosmos is revealing its secrets to those curious enough to look. This creates a kind of responsibility. If we're living during one of the rare periods when the universe is both old enough to support observers and young enough to be observable, shouldn't we make the most of it? Shouldn't we observe as much as we can, learn as much as we can, preserve that knowledge for whatever future generations might exist? Of course, on personal timescales, cosmic horizons seem infinitely far away. Whether the universe is 93 billion light-years across or infinite makes little difference to daily life. We're not going to visit the edge of the observable universe or discover what lies beyond it, but the knowledge still matters. It shapes how we see ourselves and our place in the cosmos. Understanding that we're bounded by horizons, that there are limits to what we can know, that we exist in a brief cosmic moment between the Big Bang and whatever ultimate fate awaits, all of this provides perspective. It's a perspective that's both humbling and inspiring. Humbling because it shows how small we are, how limited our knowledge, how insignificant our concerns might be in the grand cosmic scheme. But inspiring because it shows that despite these limitations, we've still managed to learn so much, to push our understanding so far, to glimpse truths about reality that seemed forever beyond human reach. The edge of the universe is also a mirror. When we look at it, we see reflected back the limits of human knowledge, but also the power of human curiosity. We see a boundary we cannot cross, but also evidence of how far we've come from our origins as barely conscious primates on a small planet. Chapter 19. The Poetry of the Edge. There's something deeply poetic about cosmic horizons. They represent not just physical boundaries but metaphysical ones, limits to observation and knowledge that resonate with ancient human themes of the known and the unknown, the visible and the hidden, the attainable and the forever beyond reach. Throughout human history, horizons have held special significance. They mark the boundary between what we know and what we don't, between safety and adventure, between home and the unknown. Ancient sailors viewed the horizon with a mixture of fear and fascination, wondering what lay beyond the edge of the known world. For centuries, maps included the warning, "Here be dragons," at their edges, marking regions about which nothing was known. These cartographic edges were temporary, pushed back by exploration and discovery. Sailors ventured beyond known horizons and found not dragons but new lands, new peoples, new opportunities. But cosmic horizons are different. They're permanent, absolute, impossible to cross no matter how advanced we become. They represent a final frontier that remains forever frontier, a boundary that expands our understanding even as it reveals the limits of understanding. This permanence gives cosmic horizons a quality that earthly horizons lack. When Columbus sailed past the edge of the known world, he discovered America. When we look toward the cosmic horizon, we can never sail past it to see what lies beyond. The horizon recedes as we approach, like a mirage in the desert, always visible but never reachable. This has inspired artists, writers, and philosophers to think about edges and boundaries in new ways. The cosmic horizon becomes a metaphor for all the things we cannot know, all the questions we cannot answer, all the experiences we cannot have. It represents the ultimate limit of human ambition and the ultimate challenge to human curiosity. Some find this limiting, even depressing. What's the point of wondering about things we can never know? Why torture ourselves with questions about what lies beyond horizons we can never cross? Wouldn't it be better to focus on what we can know, what we can observe, what we can touch and measure and understand? But others find it liberating. The existence of unknowable things, of mysteries that will never be solved, of questions that will forever remain open. This preserves a sense of wonder and possibility that might otherwise be lost. If everything could be known, if every question could be answered, the universe might feel smaller, more closed, more fully mapped with no room left for imagination. The cosmic horizon ensures that mystery remains. No matter how much we learn, there will always be more beyond our reach. No matter how far we push the boundaries of knowledge, there will always be further boundaries waiting. The universe is inexhaustible, not because it's infinite, though it might be, but because fundamental horizons limit what any observer can ever know. This interplay between knowledge and mystery is perhaps what makes cosmology so compelling. It's a field where scientists use the most rigorous mathematics and the most precise observations to probe the deepest mysteries, only to find that their discoveries reveal even deeper mysteries beyond. Every major advance in cosmology has followed this pattern. When Hubble discovered the expansion of the universe, it solved the mystery of why distant galaxies are redshifted, but created the new mystery of what caused the Big Bang. When cosmic inflation was proposed, it solved mysteries about the uniformity of the cosmic microwave background, but created the mystery of the multiverse. When dark energy was discovered, it explained the accelerating expansion, but created the mystery of what dark energy actually is. We're in a perpetual state of standing at the edge, looking beyond, catching glimpses of something vast and strange, but never seeing the whole picture. And perhaps this is exactly as it should be. Perhaps the universe is structured in such a way that consciousness, observation, and understanding can only exist at edges, bounded by horizons that define what can be known, while pointing toward limitless unknowns beyond. The poet Rainer Maria Rilke wrote, "Be patient toward all that is unsolved in your heart, and try to love the questions themselves." This attitude seems appropriate for contemplating cosmic horizons. We may never know what lies beyond the edge of the universe, but we can love the question, appreciate the mystery, and find meaning in the wondering itself. Chapter 20. The Final Horizon. As we near the end of this exploration, it's worth acknowledging one final horizon that we all face, the horizon of our own mortality. Each of us has a personal edge, a boundary beyond which our individual existence does not extend. How does this personal horizon relate to the cosmic horizons we've been discussing? In some sense, death is the ultimate horizon, the final limit to what any individual can experience or know. No matter how long we live, we'll only witness a tiny fraction of cosmic history. We're born into a universe billions of years old, and will die leaving a universe with trillions of years of history still ahead of it. This makes every human life a brief moment at the cosmic edge, a fleeting instant of awareness in the vast sweep of time. We appear, observe a tiny slice of reality, and disappear, like a wave rising briefly from the ocean before falling back. Yet this brief existence doesn't make us insignificant. In fact, the opposite might be true. The universe is vast and mostly empty, mostly unconscious. Matter and energy flow according to physical laws, stars burn and die, galaxies spiral through space, but almost none of it is observed or understood or appreciated. We're among the rare exceptions. We're matter that has become aware of itself, structures of atoms that can contemplate atoms, products of the universe that can understand the universe. For a brief moment, the cosmos observes itself through our eyes, understands itself through our minds. This perspective, sometimes called the cosmic perspective, suggests that we're not separate from the universe but part of it, temporary manifestations of the same fundamental substance and energy that makes up stars and galaxies. The atoms in your body were forged in the cores of ancient stars that exploded billions of years ago. You're literally made of stardust, as is everything you've ever touched, everyone you've ever known, every planet and moon and asteroid in our solar system. When we look out at the cosmic horizon, we're looking at structures made of the same stuff we're made of, governed by the same laws, part of the same vast interconnected whole. The edge of the universe is not separate from us but continuous with us, part of the same reality we're embedded in. This might provide some comfort when thinking about the personal horizon of death. Yes, individual consciousness ends, but the matter and energy that makes up each of us returns to the universe, recycled into new forms, continuing the cosmic dance. Nothing is truly lost. It's just transformed, rearranged, returning to the vast reservoir from which it briefly emerged. Many find this perspective meaningful, a way to connect individual existence to something larger and more enduring. We're brief patterns in the cosmic flow, temporary arrangements of matter and energy, but we're genuine parts of the cosmos, not separate from it. Our existence, however brief, represents the universe becoming conscious of itself, achieving self-awareness through us. Others find this cold comfort. They want personal persistence, individual survival beyond death, not just recycling of atoms, and that's understandable. The personal horizon of death is challenging to contemplate regardless of cosmic perspective. But perhaps the cosmic perspective at least provides context. It reminds us that limits and horizons are built into the structure of reality. We can't see beyond the cosmic horizon. We can't know what happened before the Big Bang. We can't observe other universes in the multiverse if they exist, and we can't persist as individuals forever. These limitations define the space within which we exist. They're not flaws or injustices, but features of the reality we inhabit. And within those limits, within the horizons that bound us, there's still vast room for experience, discovery, love, beauty, understanding, and meaning. The edge of the universe reminds us that everything exists within boundaries, but boundaries are not prisons. They're frames that give structure to experience, edges that define the shape of possible lives. Without horizons, without limits, existence might be formless and meaningless. It's the very fact that we're bounded, that our lives are finite, that our knowledge is limited, that gives weight and significance to what we do, what we learn, what we experience while we can. Conclusion: the infinite mystery. So what lies beyond the edge of the universe? After all this exploration, what's the answer? The truth is, we don't know. We may never know. And perhaps that's the most important thing we've learned. We've explored many possibilities. Beyond our observable universe might lie more of the same, an infinite expanse of space filled with galaxies and stars we can never see. Or it might curve back on itself, finite but unbounded. Or it might be just one bubble in an eternally inflating multiverse, surrounded by countless other bubble universes with different laws of physics. Beyond our cosmic event horizon might lie galaxies that are receding too fast for their light to ever reach us, forever beyond our observation. Beyond the Planck scale might lie a quantum foam of fluctuating space-time, or the vibrating strings of string theory, or the discrete loops quantum gravity. Beyond the boundary of mathematical description might lie aspects of reality that cannot be captured in equations, truths that exist but cannot be proven, experiences that cannot be formalized. Beyond the temporal edge at the Big Bang might lie an eternally inflating space from which our universe emerged, or a previous contracting universe that bounced into our expanding one, or a cyclic cosmos that has gone through countless iterations. Beyond the temporal edge in the far future might lie heat death, or a big rip, or vacuum decay, or something we haven't imagined yet. Beyond the anthropic edge might lie universes so different from ours that life as we understand it cannot exist, places where the fundamental constants are wrong, where chemistry doesn't work, where complexity cannot arise. Or there might be universes with different forms of life, different kinds of observers, alien modes of existence we cannot conceive. All of these possibilities are consistent with what we observe. None can be ruled out definitively. The edge of the universe is shrouded in uncertainty, bounded by fundamental limits to observation and knowledge. But this uncertainty is not a failure of science. It's a feature of reality itself. The universe has built-in horizons that limit what any observer can know. These horizons are not technological limitations that might be overcome with better instruments. They're woven into the fabric of space-time, consequences of the finite speed of light, the expansion of space, the quantum nature of reality. Understanding that there are limits to knowledge is itself a profound form of knowledge. It's a kind of wisdom, recognizing the boundaries of understanding, while still pushing against them, still exploring as far as we can go. Throughout this journey, we've seen how the question, what lies beyond the edge, branches into countless other questions, each fascinating in its own right. Is the universe infinite or finite? Is there a multiverse? What is dark energy? What happened before the Big Bang? Is information conserved across horizons? Is reality fundamentally mathematical? Can consciousness transcend material existence? These questions may not have final answers, at least not answers we can access from our position at this place and time. But asking them, exploring them, following them wherever they lead, this is what makes us human. This is what consciousness does. It wonders, it questions, it seeks to understand, even when understanding seems impossible. The edge of the universe is not just a physical boundary. It's a philosophical and existential boundary, a place where science meets mystery, where knowledge confronts its own limits, where the known universe fades into ineffable uncertainty. And perhaps that's exactly what makes it beautiful. The universe is not fully knowable, not fully comprehensible, not fully mappable. There will always be more beyond what we can see, more depth than we can fathom, more mystery than we can solve. The cosmos is inexhaustible. This inexhaustibility means that the quest for understanding can never be completed. There will always be new questions to ask, new phenomena to observe, new theories to develop. Science is not approaching some final theory of everything that will answer all questions and close all mysteries. Instead, each answer opens new questions. Each solved mystery reveals deeper mysteries beyond. The edge of the universe reminds us of this. It stands as a permanent monument to the unknown, a boundary we can approach but never cross, a horizon that recedes as we advance toward it. It challenges us to be humble about what we know while remaining curious about what we don't. In the end, the most honest answer to what lies beyond the edge of the universe might be simply mystery. Not mystery in the sense of a puzzle waiting to be solved, but mystery in the deeper sense of something that transcends our categories of understanding, something that exists beyond the reach of observation and theory. And yet, we keep looking. We keep building bigger telescopes, developing more sophisticated theories, conducting more precise experiments. We keep pushing at the boundaries, not because we expect to eliminate the mystery, but because the pushing itself is meaningful, because the quest for understanding is valuable even when complete understanding remains forever out of reach. The edge of the universe is where wonder lives. It's where the human mind confronts something larger than itself, something that puts our brief existence into cosmic perspective. It's where we realize that we're part of something vast and ancient and ongoing, something that existed long before us and will continue long after we're gone. But it's also where we realize our unique significance. We're the part of the universe that wonders about the universe. We're matter that has become conscious, atoms that can contemplate atoms, space-time that can explore space-time. We're the cosmos, examining itself, understanding itself, marveling at itself. This is perhaps the deepest truth about the edge of the universe. It's not just out there, somewhere beyond the furthest galaxies we can see. It's also in here, in the limits of our understanding, in the boundaries of our knowledge, in the horizon of our consciousness. The edge is wherever knowing ends and unknowing begins, wherever the mapped gives way to the unmapped, wherever certainty dissolves into mystery. And we live at that edge. Every person, every observer, every conscious being exists at the boundary between the known and the unknown, between what has been discovered and what remains to be discovered, between the visible and the invisible. This is both our limitation and our glory. We cannot know everything, cannot see beyond all horizons, cannot answer all questions, but we can know something. We can see beyond some horizons. We can answer some questions, and in doing so, we participate in one of the most remarkable processes in the universe, the growth of knowledge, the expansion of understanding, the illumination of darkness. The universe may be vast beyond comprehension, but we have comprehended some of it. Space may extend infinitely in all directions, but we have mapped the finite portion accessible to us. Time may flow from an unknowable beginning to an uncertain end, but we have traced much of its history from the Big Bang to the present. Reality may include countless things we cannot observe, but we have observed countless things and understood them. This is what it means to live at the edge of the universe. We dwell in a space bounded by horizons, surrounded by mystery, embedded in something far larger than ourselves. But within those boundaries, within the sphere of the observable and knowable, we find a cosmos rich with wonder, filled with beauty, governed by elegant laws we can discover and understand. So when you look up at the night sky, remember, you're looking at the edge. Every photon of starlight that reaches your eye has traveled across vast distances, carrying information from distant places and ancient times. The farthest galaxies you can see with powerful telescopes are approaching the cosmic horizon, the boundary beyond which light cannot reach us. The darkness between the stars is not empty but filled with radiation from the Big Bang, the afterglow of creation itself. And beyond what you can see, beyond what any telescope can reveal, lies more, so much more, possibly infinitely more. Regions of space too distant for their light to have reached us yet. Galaxies beyond our cosmic event horizon, forever beyond our reach. Perhaps other universes in an eternal multiverse. Perhaps structures and phenomena we haven't imagined. All of it exists, or might exist, beyond the edge of everything we know, and all of it remains forever mysterious, forever unknowable, forever beyond the boundary of observation and understanding. This is the final truth about the edge of the universe. It defines us as much as it defines the cosmos. We are finite beings in a possibly infinite reality, brief candles of consciousness in an ancient darkness, observers bounded by horizons we cannot cross. And yet we observe, we wonder, we seek to understand, we push against the boundaries, reaching always toward what lies beyond. The edge of the universe is where science meets philosophy, where knowledge meets mystery, where the human spirit confronts the infinite. It's a place of profound questions and uncertain answers, of vast possibilities and fundamental limits, of humbling insignificance and inspiring significance. It's where we stand, looking outward and inward, backward and forward, into space and into time, seeking to understand our place in a cosmos that may be far larger, far stranger, far more wonderful than we can imagine. What lies beyond the edge of the universe? Everything and nothing, infinity and emptiness, other worlds and absolute void, mathematical structures and ineffable mystery. The answer depends on which edge you're asking about, which horizon you're contemplating, which boundary you're exploring. But in all cases, in every direction, at every scale, the answer includes one constant: mystery. The universe reserves some secrets for itself, hides some truths beyond unbreachable horizons, maintains some questions that will forever remain unanswered. And that's not a tragedy, it's a gift. It ensures that wonder never dies, that curiosity always has something to pursue, that the cosmos remains endlessly fascinating no matter how much we learn about it. We live at the edge of everything we know, surrounded by everything we don't. And that's exactly where we should be, where consciousness belongs, where the human story unfolds at the boundary between the known and the unknown, the visible and the invisible, the certain and the mysterious. The universe has edges, countless edges at countless scales, but it has no end to its ability to surprise us, to challenge us, to invite us to keep exploring, keep questioning, keep wondering what lies beyond. And so we do. We keep looking up at the stars, out toward the horizon, forward into the future, inward into the fundamental nature of reality. We keep asking questions, building theories, making observations, seeking understanding, not because we expect to reach a final answer, but because the journey itself is meaningful, because curiosity is part of what makes us human, because the quest to understand the universe is also a quest to understand ourselves and our place within the vast cosmic story. The edge of the universe is calling to us, as it has always called to conscious beings, inviting us to wonder, to explore, to imagine what might lie beyond. We may never cross that final horizon, may never see what lies on the other side, but we can look toward it, think about it, dream about it, and in doing so, we honor the deepest part of our nature, the part that seeks to know, that refuses to accept ignorance when understanding might be possible, that pushes always at the boundaries of the known. This is the human condition, to live at the edge, to wonder what lies beyond, to reach always toward horizons we can never quite touch. It's a condition of permanent uncertainty and endless possibility, of profound humility and soaring ambition. The edge of the universe is our teacher, showing us both how much we've learned and how much remains to be learned. It's our challenge, inviting us to push our understanding further than ever before. It's our reminder that reality is larger than our comprehension, deeper than our theories, more mysterious than our imaginations. But it's also our inspiration. Because if there are boundaries we cannot cross, there are also boundaries we can. If there are questions we cannot answer, there are countless questions we can. If there are mysteries that will remain forever mysterious, there are also mysteries we've already solved and countless more we might solve in the future. The edge of the universe defines the limits of knowledge, but it also celebrates the power of knowledge. We've come so far from our origins, learned so much, understood so deeply. We've mapped the cosmos from the quantum foam to the cosmic horizon, from the first moments after the Big Bang to the distant future of heat death. We've discovered dark matter and dark energy, black holes and gravitational waves, cosmic inflation, and the accelerating expansion. We've done all this in just a few centuries of modern science, a few decades of sophisticated cosmology. Imagine what we might learn in the centuries and millennia to come, if we survive, if we persist, if we keep looking, keep questioning, keep wondering. The edge may recede as we approach it, but each step forward reveals new vistas, new phenomena, new questions. The journey toward understanding is infinite, but each finite step along that journey is valuable, meaningful, worth taking. So rest now with these thoughts of cosmic edges and infinite mysteries. Let your mind drift through the vast spaces we've explored together, from the observable universe to the multiverse, from the Big Bang to heat death, from quantum foam to cosmic horizons. Think about the edges that bound your own existence, the spatial horizon beyond which you cannot see, the temporal horizon of your own mortality, the cognitive horizon of what your mind can comprehend. These edges define you as surely as cosmic horizons define the universe. But think also about what lies within those edges. The capacity for wonder, for understanding, for appreciation of beauty and mystery. The ability to contemplate questions far larger than yourself, to seek truths that transcend individual existence, to participate, however briefly, in the great cosmic story. You are, for this moment, a conscious observer at the edge of everything, looking outward toward mysteries you cannot fully fathom, inward toward the mystery of consciousness itself. You are matter that has become aware, space-time that has developed the capacity to observe space-time, the universe examining itself through your eyes and mind. This is your place at the cosmic edge, your role in the great unfolding of existence. Brief, yes, limited, certainly, but also remarkable, precious, and meaningful. The edge of the universe is where you stand, right now, in this moment. It's where every conscious being stands, bounded by horizons yet reaching always beyond them, limited in knowledge yet unlimited in curiosity, finite in existence yet connected to something infinite. So look up, look out, look beyond. Wonder about what lies at the edge of everything we know. Let that wonder fill you, inspire you, humble you, elevate you. Let it remind you that you're part of something vast and ancient and ongoing, something that began with the Big Bang and will continue long after your personal light has faded. But also remember, while that light burns, while consciousness persists, while questions can still be asked and wonders still be felt, you have the extraordinary privilege of being the universe, experiencing itself, understanding itself, marveling at itself. The edge of the universe is both impossibly distant and intimately close. It's beyond the farthest galaxies and within your own awareness. It's at the limits of space and time and at the boundaries of understanding. And it's beautiful, mysterious, eternal, calling to us across the vast reaches of space and time, inviting us to keep exploring, keep wondering, keep seeking to understand what lies beyond everything we know. Thank you for taking this journey to the edge with me, for letting your imagination soar beyond the boundaries of everyday experience into realms of cosmic mystery and wonder, for contemplating questions that may have no answers but are worth asking anyway. The universe is vast beyond measure, strange beyond imagining, mysterious beyond understanding, but we are here, now, able to observe it, think about it, marvel at it, and that's perhaps the greatest mystery of all, that the cosmos has produced beings capable of wondering about the cosmos, consciousness capable of contemplating consciousness, observers who can stand at the edge of everything and ask, what lies beyond? The answer remains elusive, hidden beyond horizons we cannot cross. But the question endures, as it always has, as it always will, calling to every curious mind that looks up at the stars and wonders, what's out there? What lies beyond the edge of everything we know? The universe keeps its secrets, but it also shares enough to keep us wondering, enough to inspire awe, enough to fuel the eternal human quest for understanding. And so we continue, standing at the edge, looking beyond, dreaming of what might lie in the vast unknown that surrounds our small sphere of knowledge. The edge of the universe is where mystery lives, where wonder dwells, where the cosmos invites us to keep exploring, keep questioning, keep reaching toward horizons that recede even as we approach them. It's where you are now, in this moment, contemplating the farthest reaches of space and time. It's where you'll always be, bounded by horizons yet reaching always beyond them. And it's beautiful. Sleep well, cosmic traveler. Dream of distant galaxies and infinite possibilities, of multiverses and quantum foam, of beginnings and endings, and all the vast mystery that lies beyond the edge of everything we know. The universe is waiting, patient and eternal, ready to reveal its secrets to those curious enough to seek them, brave enough to stand at the edge and look beyond. Good night, and may your dreams carry you to the furthest reaches of space and time, to the very edge of existence itself, where the known universe fades into infinite mystery and endless possibility.